Swayam Prabha. Digital India. Educated India.
Welcome all of you to these fluid mechanics lectures. As I want to say, this is the last lectures for this series of the lectures for these 8 weeks and 20 hours lecture series on the fluid mechanics. So, let us have a talking about the books. Again, I want to repeat you that let us follow the some of the books, okay, which is highlighted here. Mostly again I have to repeat it if you want to have the basic concept and understanding the fluid mechanics as a illustrations wise the fluid flow characteristics. Please read the books written by Sinjal Simbala, Fluid Mechanics Fundamentals and Applications, FM White books, and IH Same's books, Mechanics of the Fluids. Please go through these books which are really quite interesting way written the fluid mechanics from introductory level to the advanced level. Now, let us come back to today's contents, what I am going to deliver to you. Very interesting experiments which was conducted almost 70 years back. That is what we will be discussed here, and the new experiment what we are conducting at IIT Guwahati as a glimpse I will show to you. Then we will talk about 3 things: non-circular conduits, how we can apply the same equations for non-circular conduits, and we also will talk about how does velocity vary in a pipe flow and how to compute wall shear stress at the boundary. And also we will talk about how to solve the multi-path pipe flows, and then we will solve some of the gate questions on the fluid flow through pipes, and we will have the summary. Now, let us coming to the previous lectures, the recap of the previous lectures. As shown in these figures, whenever you have any pipe flow components with like a pumping systems, the reservoirs, please draw energy gradient line and the hydraulic gradient line. Those two lines will indicates us where the energy loss is happening it and where the energy gaining is happening it. For example, if you talk about the pump, because of these pump resistance we have getting a extra energy to the fluid flow through the pipe systems. So, that is the reasons again I am to repeat it to tell it. First you draw a datum and you have the reservoirs, and from that reservoir you start drawing the energy gradient line, also the hydraulic gradient line. The hydraulic gradient line, energy gradient line, the difference will be the velocity head. That is what is the V square by 2g, the velocity head. So, any datum I can have a Z is potential head, then I have the pressure head, then I have the velocity head. So, these 3 components I can draw the lines like this. For example, if you look at these diagrams, from the reservoirs you do not have any velocity components. That is the reasons you have a hydraulic gradient and energy gradients both coincident at that locations. As you go, there is a energy losses, and through this energy losses what it happens in pipe, that is what we call major losses, and the bends entry point and exit point we call minor losses. And these losses already we quantified in the last class. And as you know it, the hydraulic gradient lines drop of this hydraulic gradient line or the energy gradient line because of the dropping of the potential energy from these pipe orientations. Again, if you look it, there is a major losses, there is a pumping system is there which is giving extra energy or energy head to this. That is the reasons again you have velocity head and this. So, whenever you have a pipe flow problems, try to sketch approximately energy gradient line and the velocity hydraulic gradient line. As you draw the energy gradient line and the hydraulic gradient line, you can try to understand how the flow taking place, where the energy losses are happening it, whether the major losses, the minor losses or adding the energy to the system, all you should identify it when you drawing this energy gradient line, hydraulic gradient line. Now, let us come back to very interesting experiments what it happened in 1930s, okay, much before the World War II. Okay. The Germans, the professor used to do a simple experiments, okay, which one of classical experiment conducted in a pipe flows and which helped to make this complex flow to a simpler empirical based energy loss quantifications, velocity distributions quantifications, as well what could be the wall shear stress. If you look at this, any of the pipe flow, we can have a laminar flow, the turbulent flow or the transitional in between the laminar and the turbulent flow. The experiment is conducted by the Nicaragua is that with having very simple concept that the pipe put it with a roughness, this equivalent roughness is from the sand grains, which the figure is shown it with a zoomed with a 20 times. That means, you can see that is quite random, the sand grains are roughened it or put it here such a way that it can create a roughness on the wall of the pipe. If you have that roughness which representing is R, the roughness height representing as R and R is the radius of the pipe flow. So, you can know it that because of this roughness your flow characteristic can change it. Also we know very well the Reynolds numbers also control the flow behaviors. So, that way to know it what is will be the wall stress, the tau value, what could be the velocity distributions, what could be the energy losses when you have a pipe length of L with the informations about the roughness, informations about the flow Reynolds numbers. Those was the basic question was there before starting the experiment by Nicaragua's experiment setup, which is very basic experiment setup. You can see it is from this very basic experiment setup, having the big water tank connected with a pump and having a test sections in here which measure the velocities and all. And if you look at the dimensions of these water tanks, which is 6.5 meter tall, 1.5 meters diameters. So, you can look at that how precisely experiments were conducted to quantify what could be the energy losses and what could be the velocity distributions and what could be the relationship of velocity distributions with wall shear stress. As you can understand from this experiment what was conducted in 1930s, it is quite remarkable way we got it big relationships for the turbulent rough pipes, that you have a friction factors and you have the flow Reynolds numbers, which gives us a very three reasons. One is if you have a R is too large and the Reynolds numbers too large, you can have a friction factor is a function of R by D, that means roughness factors. R by D is a response factor, and when you have flow is laminar, it is a function of the Reynolds numbers. And if you have a smooth pipe where the roughness is very small, roughness is the factors is much slow, very small, then you can have the smooth R values, the R is a very small, then you can follow this Blasius equations, which is a functions of the Reynolds numbers. So, now if you look at that, by conducting a series of experiments, but Nicaredos finally bring the friction factors relations with the Reynolds numbers, which is Modi charge, and we have been using that for designing all these pipe flow networks for the industry, the water supply, sewage treatment plant, all where we are using the same equations what was developed way back in 1930s, conducting a series of experiment for turbulent rough pipes, which is very complex still now to do in a CFD simulations. Now, if you come back to that, what we have been doing at IIT Guwahati, we also do similar sort of creating the roughness in open channel flow. That is what you can see, this vegetations are there. Some degree of we are creating the roughness, and we try to measure the velocity distribution, try to quantify the wall shear stress, what could be there, bed shear stress could be there, all we are quantifying, measuring the velocity distributions, measuring the water slope. And what we have? We have introduced the roughness, and you can see these roughness behaviors and how the flow dispersions are happening with putting the color dyes. I am not going much detail on that, but if you look at it, for this case, if the flow is a submerged conditions and you have the roughness like this, there are the vortex, the eddies formations and the strength of eddies formations, you can get it, and that is what we got it, conducting a series of experiments in this flow as well this flow. So, what I am to tell you that the experiments gives us a lot of confidence of a very complex problems like a turbulent flow in a rough pipes, which is very difficult to model as of now also in the CFD softwares, but we can conduct a series of experiment and we can establish the empirical relationship, and those empirical relationship is used in generally in industry to design the pipe networks. Now, coming to the other case, many of the times also we do not go for only the circular conduits or the circular pipes from one point to other points. Okay. But when you go for a non-circular case, you need to define as a edge equivalent flow. Okay. So, that means we introduce a hydraulic diameters. Okay. It is called is hydraulic diameters, which is a functions of area and weighted perimeters. The part of the perimeter which is under weighted conditions, weighted perimeters. Like for example, if I have the flow of pipes, it is going through pool. So, that way the total perimeter I can consider as weighted perimeter. But if I have the flow half filled, the pipe flow is going it, then I will consider the weighted part of this one only. I will consider the weighted perimeter. I am just highlighting that we need to consider weighted perimeters, the area, then we can compute the hydraulic diameters. Okay, as equivalent diameter we can get it. That is what for the circular sections, if you just substitute, if the D is a diameters and the perimeter for the full flow of these pipe systems, you will get it hydraulic diameter in a circular pipe when it contains full of waters, okay, full of liquid what is flowing through that, then you can get it the hydraulic diameter as equal to the geometric diameters. So, that what is equal components comes for that. Please do not be confused. The diameter, hydraulic diameter as a equivalent diameter representing for other non-circular conduits. Now, come back to the non-circular conduit, like you may have a conditions where you have a only flow through these ones, okay. That is called circular annulus diameters. You have a D1, D2 and you have a flow through these ones. So, you can easily find out what will be the flow area and what will be the weighted parameters for both the cases. That is what will give it this one. Similar way, if I have a rectangular cross sections and flow through these systems, I can define it what will be the area and the weighted parameters. That is what will give me the hydraulics diameters. If you have a isosceles triangles with a 2 alpha degrees between radius r, also I can put it numerically what could be the area, what could be the perimeters, and I can get it for these ones. Now, let us come back that when you have a non-circular pipes, like if you have a pipe like a triangular shape. Okay. So, in this case what will happen, if you have a laminar flow, you will have a wall stress will be maximum near the midpoints of the sides. It will have a maximum at the midpoint of the side, wall shear stress becomes will be 0 at this point, 0 at this point. Okay. So, more details I am not going it because it is quite undergraduate level and we did not discuss much detail of the flow patterns, okay, what supposed to be there when you have the complex geometry like a isosceles triangles, that you can see that the more maximum wall stress will develop at this point, well it will be 0 at these 3 points. Now, if you look at that, if you have the turbulent flow, same case you have a turbulent flow, the velocity distributions as well as the wall shear stress distributions exchanges it. What we do it, even in case of the turbulent flow, we also use the Moody's diagrams, hydraulic diameters replacing with a D, that is what is used to quantify what could be the energy losses. The wall shear stress is 0 at the corner, as already we tell it in laminar cases. So, we will have a wall shear stress at the corners is 0, but along the side the wall shear stress is close to being the uniform. This side you will have a uniform, not the maximum at the midpoint as you got in case of laminar flow. So, that is the flow behaviors what is observed by conducting a series of experiment, quantifying the velocity distributions, knowing it what could be the wall shear stress. Now, if you look at that, when you have this type of flow, always you can have this type of vortex formations. Okay. This type of vortex formations you can see it, and these vortex formations we call the secondary flow generations, what it happens it, and these are responsible for the mass exchange, momentum exchange through the flow systems. So, as you go from away from these circular pipes, for this case like a triangular flow zones, you have a more complicated the velocity distribution, shear stress distribution as compared to the circular pipes as a symmetrical problems what we try to understand it. Now, coming back to the turbulent flow, again we can follow the same head loss equations. The head loss is a functions of the velocity head, which is the L by dH, the dH is here, the hydraulic radius, and L is the length, F is the friction factors, and we can compute what is the energy losses. Most of the often we use these because this is what is gives the energy losses in terms of meter, but we can use these functions which is gives us in terms of Newton meter per kg. So, we divide by the acceleration due to gravity, we will get in terms of meter. Now, coming back to the velocity profile or the shear stress at the boundary. Here we divide into 2 zones as suggested by Nicarodos by conducting a series of experiment finding out velocity profiles for the turbulent flow, where you have the flow Reynolds number less than 3 millions. Okay, if you look at this Reynolds numbers, okay, it's too large. Okay, but because as I said it earlier, the experiment setup was designed such a way that he could conduct the experiment which will have a flow Reynolds numbers in the range of 3 millions, more than that. By conducting this experiment, what he got it that the non-dimensional velocity distribution B by B max starting from here is 0, it is a wall, and this is the at r equal to 0, that means it is the center points. If you plot y by r, okay, and b by b max, no doubt the velocity distribution for laminar flow is follows this ones. This is the laminar flow. But as increase the Reynolds numbers, okay, as increase the Reynolds number, it goes up to this, you can go to up to 3.24 order of million scales. If you look at that, the velocity distributions as going more platter to platters. Okay, that's the very uniqueness it comes it. In case of the laminar flow, you will have a velocity distribution like this, but in case of the turbulent flow, you will change the velocity distributions as we increase this flow Reynolds numbers. So, to quantify what could be the relationship for this type of velocity distribution B by B max, it establishes a relationship with y by d by 2 or y by radius by 1 by n. It is fitted with a data curve, and finally find out the n varies with the Reynolds numbers. Its range from to 6 to 10 for the Reynolds numbers from 4,000 to the 3.2 million. So, in this case n varies considerably from the 6 to 10. So, this n is a function of Reynolds numbers. Okay. But many of the case also n is considered is 7. So, many of the time is called 1 by 7th rules for describing the velocity distributions in a 5 flow for turbulent regions. But when you look at what could be the shear stress, that is what is the wall shear stress at the wall of the pipe. That is what is also empirically established with a functions of wall stress, the average velocities, and hydraulic radius and V. That is what is developed it to compute it what could be the wall stress from experimental data set. From experimental data set, it derived, that is the reason called empirical studies. The wall stress, the relations with the average velocities and the kinematic viscosities and the R value, that is giving the what could be the wall stress for a circular pipe. Now, if you look at that, when you go for higher Reynolds numbers turbulent flow, higher Reynolds number turbulent flow, which is more than 3 million, the Reynolds number is more than 3 millions. In this case, what it actually happens is, I am not going more details. When you have the Reynolds numbers more than 3 millions, then there is certain zone of the velocity profiles develops. Like at the wall, you can see there will be a flow which behave like the laminar flow, which behave like viscous sublayers. And you go outer of zones, you will see that will be a velocity profile will be developed, which is not the linear relationship between. In laminar flow, there is a linear relationship between the shear stress and the velocity distribution, but that does not happen it when you go for the outer zones. And in between there is a overlap zones formations. In this lecture, we are not going more details because I have not introduced you boundary layer concept, but try to understand it. When you go for higher Reynolds numbers flow, you will have a very small thickness near to the wall where the flow behaves like a layer, where the viscous is dominated too much, and that is the reason you will have a viscous sublayer zones. But as you go far away from the wall, you will have it where it will have a turbulent velocity profile zones, which experimentally established that change of regions will happen as we go from the wall. Most of the times this type of things, as I said it earlier, we do a non-dimensional analysis and then we try to establish the relationship with dependent variable or independent variable. For this case, if velocity distributions is considered as a functions of shear stress, wall shear stress, mu, rho and y. Y is the distance from the wall. And if you do a simple dimensional analysis, we can compute like this. This is a simple dimensional analysis. To rearrange the terms, you will get a friction velocity or the shear velocity in terms of wall stress. In terms of wall shear stress, we will get it this value. So, this is the relationship. We do not know this F value, and from the experiment we found that F value is just a linear function, okay, just a linear function, it does not have any. So, we can find out the Vx by stars is this way in the regions which is near to the wall. Okay. This is the regions near to the law at the wall, which is very simple as a Vx by V star is representing this friction velocity is a simple y by V star by kinematic viscosity. But if you go to the outer layers where we look at that a velocity defect concept, how far the velocity from average velocity, that the defect means how much deviations, how much difference between that. If you look at that and looking a functional relationship with your shear stress H, rho and y, we again will get the similar functions from the dimensional analysis between V and y and h. Now, if you look at that, if you put it high turbulent flow and the velocity, the regions is this is called velocity deflect rho, and h is replaced by the r, the pipe radius, then you can have these experimentally derived components, and this alpha will represent equal to the 0.4, and this is what the average velocity or time average velocity components, and this is a spatial average velocity component, how they are fluctuating with shear velocity, and more details if you in the overlap zones you will have this equation. So, now if you look at from the experiment and the dimensional analysis using this Necker-Roeder's experiment data set, it was found what could be the alpha value, okay, which is here is 0.4, and for the overlap zones alpha beta at a different value, and here I am not talking much more, it is called the logarithmic overlap layers. Okay. In between these two regions we can look at how the velocity distributions is taking it. Now, we coming back to the very simple examples, okay, and that is what is in your textbook is necessary to for. If you look at that, many of the times you have the pipes in series, pipes in parallel, or three reservoir junction problems. Okay. Pipe in a series are very simple problems like electric circuits. Okay. You can have a series of wires, you have wires from point A to B. Okay. If you have a that, definitely the discharge will be for a steady state conditions, for steady flow conditions. So, discharge at the Q1, Q2, Q3, that should be equivalent because it is a steady state. But if you are having an energy losses between delta H1 is energy losses for these regions, this is delta H2 is energy losses, this is delta H3 is energy losses. The total energy losses will be the delta H1, delta H2 this. So, this pipe in series a very simple problems in which your flow is a constant, okay, but the total head loss is a sum of the head losses of individual pipes is connected in a series, very simple problems. But when you have a pipe in a series, please remember it that you always should consider whether there is a minor losses. There is major losses which is the frictional losses component for the pipe 1, also there will be a minor losses because the change of the diameter of the pipe, okay, there will be expansion or the contraction, exit loss, entry losses, all the loss component you have to look at which way the flow is happening it, and you can quantify what could be the minor losses. So, this is the major loss plus minor loss, that is what is representing here for the pipe 1, this is representing for the pipe 2, and this is representing for pipe 3. So, similarly, if you have more number of pipes, you can have a just summations of the head loss, the head energy losses along the pipe from pipe 1, pipe 2, pipe 3. Most of the times if you look at, because the same discharge is going through that, you will have the V2 and V3 which is a functions with a discharge is same, it will have a proportionality with a V1. So, you can write a simple formula like this, okay, V1 square 2G can come it and can have a constants with this value. So, these are very shortcut way to do it, but I always encourage you please follow this, the energy losses computations for major losses, minor losses, major losses, minor losses, and compute total, then find out what could be the energy losses happening in a pipe in series conditions. Now, if you look at another very simple problems, that pipes in parallel. When you have a pipe in the parallels, you can understand it. See, if I have the pipe in the parallels, there are 3 pipes are connected here. This is the A is entry point, B is exit point. From this point to this point, the total energy losses passing through this path A or path B or path C, that should be equal. So, energy losses should be equal, whether it follows path A, path B or path C, all the energy losses should be equal, that is the conditions. And as the flow is coming and divided into 3 parts, we can always write the Q what is coming, it will be distributed into the 3 parts in these figures. So, as you have a branching out, as you are converging it, you can write the Q1, Q2, Q3, and the QB will be the sum of Q1, Q2, Q3. So, sum of the discharge will give us the discharge what is passing through the A or B, and the energy losses whether following the 1 path, 2 path or 3 path should be equal. Then the energy at these 2 points will be come to a the same values, although it not be possible to have a different energy losses, that cannot be happen in a flow systems. Now, if you look at the 3 reservoir junction problems, which many of the time it is given, see that you have a multiple reservoirs, okay. You may have the multiple water tanks are there and connected to the 5 flow systems, and you have a junctions where you have a 3 are connected here. Out of these 3 flow, one could be also outflow. We do not know that which direction it will be outflow it, but we can say that sum of the Q discharge should be equal to 0 at this point. There is no outlet. Okay. So, at the junction point, the continuity equations or mass conservations at these equations should be equal to 0. But another one what you have to need to compute it, how much of energy or the head is, what is the elevations of hydraulic gradient line, that is what it will be Z1, and this the pressure head part what will come it. this hydraulic gradient is supposed to be equal to yours the change of energy. We have this energy gradient line at this point like this, and I know these hydraulic gradient lines at these points. If I looking at how much of head loss is happening, because the pressure head is equal to 0 here, the velocity head equal to 0 here. So, this is energy gradient line, also the hydraulic gradient line. So, that way if I look at this, the line of hydraulic gradient line, not the energy gradient line, line of hydraulic gradient line, because I am not looking the velocity point, that should be equal at this point after having the energy losses. That is what is Z1 minus HF should be energy losses. Similarly, Z2 HF it should be energy losses, Z3 HF should be energy losses. So, how much of energy losses will happen in such a way that we will have a hydraulic gradient at the junctions will be these ones. That is what we apply with a loss and compute what is the head losses should be there in this direction, in this direction and in this direction. Okay. And based on that we can compute that what will be the flow contributions, a Q1 or Q2 and Q3 directions. So, you have a 3 equations here as well as these equations help us to find out the flow directions and the head losses of a 3 reservoir junctions problems. Okay. This is quite interesting problems, but try to understand that we are computing the hydraulic gradient line and what is the hydraulic gradient locations of at the junctions, and based on that we are just equating the energy losses to compute that part. That is what the basic component. Now, come back to a example 1, which is a GATE 2014 questions paper, which looks like very lengthy, but it is a very simple problems. Okay. An incompressible fluid flowing through a steady rate in a horizontal pipe. Okay. From a section, the pipe is divided into 2 horizontal pipes as given the D1 and D2. Okay. And D1 is 4 times of D2 run for a distance L each other, then again join back to pipe of the original size. Okay. You just sketch the problems. Okay. Many of the times please sketch the problems, then you can understand it. For both the parallel pipe, assume the head loss due to the frictions only, that is the US friction factor to be same. So, F is a constant, F is constant. What could be the velocity ratio between bigger and smaller branched pipe is? Okay. If you look at these problems, as we solved earlier, we follow this basic concept of one dimensional steady flow incompresses this, neglecting the minor losses, only the frictions losses to be considered. As is the parallel pipes flow, you know these head losses of this path pipe 1 and pipe 2 should be equal. This is a very simple thing. F is a constant and the head losses between either the pipe 1 or pipe 2 should be equal. Based on that you can compute what could be the D1, D2. Ratio is known to us, we have to compute the velocity ratio. Now, if you look at this way, it is very simple things that you know it had losses between section and 1, 2 for these two. If I equate it, I will get it the ratio of the velocity. That is what is the problem. Okay. Even if I do not need continuity equations to show it, only with help of the head losses between section A and 2 being a parallel pipe, that should be equal, and that is what if you equate it, I will get the ratio between the velocity V1 and V2. Okay. That is the point what we will derive. Another problems which GATE 2014 questions also, a straight 100-meter long raw water, okay, this is only waters, gravity man is carry the water from intake to a jack well, okay, of a water treatment plant. Okay. So, basically there is an intake, it takes the water from the rivers or groundwaters and go to a well which is called the jack well, where basic screening and all things done it, and then go for the water treatment plant. Required flow through the water main is given to us. The allowable velocity is given to us 0.75 meter per second, F is given, G is given to us. The minimum gradient, what could be the minimum gradient to be given to the main, so that it require amount of flow without any difficulties. Okay. You just sketch the problems. The problem is the 100 meters, there is a intake, this is the jack, there the Q is given to us, and also it is given the allowable velocity, means this is the maximum velocity can go through this pipe. What is looking at, what could be the minimum gradient to given to this pipe, so that the required amount of water can go to the jack well from the intake well. The problems, if you look at it, looks very difficult, but it is not that. What is looking at that, how much of energy losses is happening it when flow is going from A to B because of frictional losses, how much of energy losses is happening it. Whether we can put a gradient such a way that it can make a flow maintain it. That means, you compute the energy losses, multiply it with the length, that what will gives us totally energy loss what is happening it. And if I know the total energy losses, then I can know it what could be the gradient or the potential energy head I have to provide it to have this flow system. Again I need to repeat these things to tell it that the problem is frame it bit different way, but try to understand it. What is looking at that, what could be the minimum gradient to be given to this flow, so that water can flow from this point intake to the jack well. That means, when flow is going through this pipe, there will be frictional losses, the energy losses due to the pipe frictions. Those frictions should be, energy losses should be overtaken by the potential energy gradient what we have to keep it. That is the problem. So, potential energy gradient to be provided with respect to the energy losses what is going to happen it. If you do not provide minimum gradient, then water will not flow through that. That is the very basic concept here, that minimum gradient is to provide such as that it accommodates the frictional loss. Okay. That is the trick of the problem. Since the velocity is given, the Q is given, we know what could be the diameters using the continuity equations, very simple things. And you also know it what could be the energy losses in terms of meter, just substituting these values, okay, you can get it what could be the energy losses. Then the minimum gradient what you are looking, this the gradient is necessary to have flow from intake to jack well. Let us start this third examples, which is gives that 2 kilometer long pipe with a diameter of 0.2 meter diameter connects two reservoirs as given in the figures. The difference between the water levels in the reservoir is 8 meters. That means, the energy losses between two reservoir is 8 meters. That is where friction factor is given to us, which is 0.04. Accounting friction, entry and the exit losses, we have to estimate the average velocity of the flow. So, that way we can say it, the flow will take place with having total energy losses of 8 meters, and difference between these energy losses will account for major losses, which is a friction losses. The minor losses here is the entry and the exit losses. That is what the additional things what we will consider it, but other losses will not consider this case as given in the problems. So, the friction factors data what is given it, length of the pipe, the diameters and the total head losses. The loss coefficient in terms of velocity head, as you know it, at the exit we consider as 1, at the entry we consider 0.5. The half of the velocity head losses at the entry levels, and at the exit level total velocity head what we lost it at the exit level. This is 1, this is 1.5. Now, we will apply the Darcy-Weisbach equations to compute what is the energy losses for the major losses or the pipe flow because of the friction components, and the minor losses here is entry and the exit losses. That is what is the coefficients we use in terms of velocity head, and here we have considered 0.5 and the 1. By substituting these, and we can get it the big series of equations like this, and substituting the value you will get a quadratic functions, and solving that you will get the velocity. So, if you look at these problems, it is quite easy, only you have to remember about the coefficients, the factors what you use it, the loss coefficient are factors what you use for computing the entry loss and the exit loss. The exit loss is total velocity head, half of the velocity head we use it to as a loss at the entry level. That is the things, otherwise this problem is quite a numerical problems to solve these ones. The last examples, let us have a, it is slight bit a design problems could be consider it, where you have the two reservoirs, okay, you have an entrance and exit, the water density and the dynamic kinematic viscosity is given to us. The two reservoirs having the discharge 120 meter long, 5 centimeter diameter pipe, several minor losses can happen it, like a valve losses, there is a pumping systems here, there is a band, there is a elbow, there is a half open valve gate, the exit and entrance, all the losses can be there. If a roughness ratio of this pipe is given, it is this part, compute the pump horsepower required, and the K value given for the bend is 0.25, regular 90-degree elbow is 0.95, open globe valve is 6.9, half closed gate valve is 2.7. Entry and exit already we discussed what could be the loss coefficients. So, that way we need to compute how much of energy is required the pumping at the pump, so that we can have a these conditions, which is a 6 meter, this is the 36 meters, the difference between them is 30 meters. So, here we have a major losses, we have a minor losses. So, as usual you will have a flow classifications, in this case one dimensional flow and all, and here you have a frictional losses and you have a losses what you have considered for the entrance, valve, band, elbow, half and exit phase. So, these all the losses components are given it, and we are looking at what could be the pumping requirements. Since here the roughness factor is given to us, we need to compute the friction factors from Modi's charts, which needs Reynolds numbers. So, first let us compute what will be the average velocity and what could be the Reynolds numbers for this flow. Diameter is given, velocities, then we can get this. So, these Reynolds numbers with these roughness factors we will get it from Modi's charts, the value of friction factor. This is what in generally design we do it to compute the Reynolds numbers. Then we for a given roughness factors we can compute it what will be the or get this from chart what will be the friction factors value. Then we can account for all the loss components in terms of velocity head, that entry, the valve, bend, elbow, half valve and exit, which will be 12.3 in terms of velocity head. This is the factors, the sum of the factors whatever energy losses factors we are adding it, starting from entry is 0.5, exit is 1 and this value is given to us, and mostly in a tabular forms are available to us by conducting a series of experiment. Any of the industry, they give this value, what is the range of the energy loss coefficients for the bend, valve, elbow. It is given in generally in any pipe manufacturing company. Now, if you will go to the next, what we will do it is very simple things, that we are applying these energy equations, head loss and this part. Since two part V 1 V 2, if I put the energy losses V 1 V 2 is 0, and solving this pumping head, okay, which is will give it the elevations difference and the major and the minor losses component, then I will get it what is the head requirement at the pump, which is coming out to be 57 meter. Okay. So, this is the loss component and this is what the elevation, the potential head what we need it from 6 meter to 36 meters, that what is coming off. So, for lifting of 57 meters, how much of power we requirement? It is there, which is very simple things for us to compute is that rho g q h p. Okay. So, you know it what is the power requirement to lift this much of mass of the flow, rho and q, that is weight mass flux into the h p, that what will give us the power. In terms of h p, we will get it 4.3 h p power requirement is necessary to lift the water up 57 meters. And if I consider any pumping centers, we have this efficient, how much of efficiency 70 to 80%. You cannot have a 100% efficiency. Considering that this 4.3 HP power and designing parts of that, we can consider the 6 HP pipe pump is enough for this pipe flow, this system of two reservoir connecting with a 30 meter difference and energy losses what it will be accounted for. So, this way we generally use a design problem to solve the problem, do the designing of the piping system, additional energy like a pumping, or in a hydropower projects we put it turbines and all. The basic concept what you use is the energy gradient lines, the Modi's charts and that's is specific equations to solve this problem. With this, let me summarize these problems lectures what I discussed today. Starting from the 1930s, Ricardo's experiment, which is one of the finest experiments conducted way back in 1930s, and that was given us very complex problems like a turbulent flow in a rough pipes and as equivalent energy losses in terms of friction factors, and establish the relations, which is quite interesting and quite inspiring to us to know that a series of experiment can help us to understand very complex flow, turbulent flow in rough pipes. We also shown this just examples that similar type of experiment we have been conducting at IIT Guwahati. I discuss about non-circular pipes. We also discuss about very introductory levels, because we didn't discuss much about boundary layer concept or turbulent flow much details in these 8-week classes. So, I just give you a introductory levels to know it, how the velocity profiles that, and we at the last we talk about the multi-path pipe flow, pipe in series, parallel or the 3 junctions, and we solve the 4 examples. So, with this I wish to conclude this 8 weeks and 20 hours lectures on the fluid mechanics. We cover all these topics and very beautiful illustrations, the PPT and all the blogs what you are doing it all, they are helping my 3 PhD students. Okay. And I do acknowledge their effort for developing this course seamlessly and ending this part. Let me conclude with this quote: a man is that the product of his thoughts. what he thinks he becomes. With this note, I can see that NPTEL course is giving you opportunity to think beyond what you thought, okay? And that's what should look at, that this course will tell you, will inspire you to for the next level. With this, thank you a lot to have this almost 23 hours lectures hearing from us. Thank you a lot.